some polynomials are just power functions. You just have a single power, say x to the 6 or x squared or x to the 4. Here's some pictures of graphs of those functions. If you have x to a positive integer power, then it's either an even or an odd function. If the power is even, then it's an even function, and therefore it has this symmetry in the y-axis, and it looks something like this. We have the parabola for y equals x squared, and then as the powers go up it gets steeper, x to the 4, x to the 6. They're no longer parabolas, but they have this bowl-shaped graph. If the power is odd, so if you have an odd integer power, then the function is odd. For the positive powers, it looks a bit like this. It looks kind of like x cubed, except as the powers go up, the functions get steeper. Now recall that we have other power functions. For example, the square root function is x to the 1 over 2, and that looks a bit like this. It increases more rapidly near the origin, and then it kind of flattens out as you head off to infinity. And remember, we said that if n is even, the domain of x to the 1 over n is all x values which are greater than or equal to 0. And as you increase the n, the function increases more rapidly for x less than 1, and then it flattens out more quickly than the square root for x bigger than 1. Now, if n is odd, x to the 1 over n has a domain which is all real numbers. Again, it's an odd function. It has symmetry in the origin, and it looks a bit like x to the 1 over 3, and it looks almost vertical at the origin. For higher values of n, the function is flatter if the absolute value of x is bigger than 1. For negative powers of x, negative integer powers, we have two here. 1 over x is not defined for x equals 0. Neither is 1 over x squared. Again, x to the minus n is even if n is even, and it's odd if n is odd. So it has symmetry through the y-axis if n is even, such as y equals 1 over x squared here, and it has symmetry through the origin if n is odd, such as x to the minus 1 here. Another type of function which we will have a lot to do with in this course is a rational function. This is a function that looks like a polynomial over a polynomial. And remember, the domains of these functions are all x values, so that the denominator is not equal to 0. And later, when we have the derivative in our toolbox, we'll spend a good deal of time graphing these functions. An algebraic function is one that's put together from x's and any combination of algebraic operations, including taking powers and roots. So you can add anything, multiply, divide, take powers, take nth roots, and this gives you an algebraic function. Here are a few examples. This one isn't quite a rational function because it has the x to the power of 2 over 3 here in the middle, so the numerator isn't a polynomial. But that's an algebraic function. It fits into that category. And g of x is again not a rational function because it has the square root of x here in the denominator, but it also fits into the category of an algebraic function because it's constructed from x's and numbers and minuses and divisions and plus and the square root. This one again comes from physics. It models the mass of an object, and that's an algebraic function of a few variables: the velocity relative to the observer, its resting mass, and the speed of light, which is a constant.